Hey, welcome back to your favorite pre-calculus class. We're going to talk about exponential functions, um, define those, and take a look at the graphs and evaluate as well. Let me blow this up here. So, just to remind you, here's some laws of the exponents. A to the s times a to the t is a to the s plus t. These two, everybody seems to get mixed up. Also, don't forget anything to the 0 power is 1. So you got your rules there. Here's just a couple. 4 to the negative 2. Anything negative exponent means you take it down. 1 over 4 squares. What that is, you got 1 over 16. 27 to 2/3. You want to write that as the third root of 27 to the second power, because 1/3 times 2 is 2/3. So you take the third root of 27 and then you square it. So you're looking for 3 of a kind because you're taking a third root. Well, 27 is 9 times 3. In other words, 3 times 3 times 3. Again, a third root, you're looking for 3 of a kind, if you will, right? So that's a 3. 3 comes out. OGL, and 3 squared is 9. So 27 to 2/3 is 9. All right, let's get into an exponential function. So an exponential function is anything of the form c times a to the x. C is just a constant in front. A is your base, or your growth factor. And x, you're going to take it to the x power. So let's look at an example here. Y equals 2 to the x. Well, your constant is in front. They're not showing that as 1 times 2 to the x. So c is your constant. So it's just y equals 2 to the x. You don't write the 1 here. So we're going to plot some points here. So let's start with 0. Well, 2 to the 0, anything to the 0 is 1. Let's plug 1 in. 2 to the 1, of course, is 2. Let's plug 2 in for x. 2 squared is 4. Let's plug 3 in for x. 2 to the third. 2 times 2 times 2 is 8. 2 to the fourth. 2 times 2 times 2 times 2 is 16. And we could keep going with that. We're also going to graph this. In fact, let's go ahead and graph those points. We got 0, 1. We got 1, comma 2, 2, 0, 1, 1, 2, 2, 4. We got 3, 8. It's up there. Now let's go to the left. Let's plug in negative 1, negative 2, negative 3, and so on. So 2 to the negative 1, 2 to the negative 1 is 1 over 2 to the 1, so 1/2. 2 to the negative 2 is 1 over 2 squared, so 1/4. 2 to the negative 3 is 1 over 2 to the third, so 1/8. 1/8, that's a really bad 8. And so on. So we got negative 1, I'm up halfway. Negative 2, I'm only up a fourth of the way. Gosh dang this thing, draw on it. Up a fourth of the way. Negative 3, I'm only up an eighth of the way, and so on. Anyway, soon up we draw this thing. And there's our y equals 2 to the x function. Now notice as we go to the left, this thing gets closer and closer and closer. As this goes to negative infinity, the y values get closer and closer to 0. So we've got this horizontal asymptote. There's your definition of a horizontal asymptote. Y equals 0. As x goes to negative infinity or positive infinity, as it increases in magnitude, if you're approaching a y value, you've got the horizontal asymptote. So in this case, you're actually not going to cross that horizontal asymptote, y equals 0. Your domain here is going to be all real numbers, so negative infinity to positive infinity. Your range is simply above that horizontal asymptote. So from 0, we're not touching 0 to positive infinity on this thing. Okay. There's a little nicer look at that. That's your horizontal asymptote there in red. So how do you tell if you have an exponential function from, let's say, a table of values? Well, what's going to happen is if you take the next term divided by its previous term, if you will, you're going to get a constant growth. You're going to get the growth factor every time. Okay, or another way to write it is f of x plus 1 equals a times f of x. So for example here, we're going to check if these things are linear, exponential, or neither, okay? And so what we're going to do is we're going to take f of x plus 1. Let's look at this one for just a second. We're going to take f of x plus 1, so that's the 2. We're going to take f of x plus 1 over f of x, and it's got to equal a every time, okay? So, for example, if your x is -1, so let's start with an x value of -1. F of -1 plus 1 over f of -1. In other words, f of 0 over f of -1. So the next one, y value, which is 2, over its previous y value, which is 5. So we're claiming that it's 2/5. Now it's got to be the same every time. So now when I let the x value be 0, now I'm going to take -1 over 2. Well, the first time I got 2/5. And then the second time I get it, I got -1/2. It's got to be the same every time. So this is not exponential. This one's not exponential. Okay, whereas over here, if I go 16 over 32, I'm getting a half. It's got to be the same as 8 over 16. Well, 8 over 16 is still a half. That's got to be the same as 4 over 8. 4 over 8 is still a half. It's got to be the same as 2 over 4, which is still a half. So this one, yes, is exponential. How about over here? Is 4 over 2 is 2. Well, that's not the same as 7 over 4. So this one's not exponential. So then the question becomes, well, are either A or C, are those things linear at all? Well, if they're linear, then you've got to have a fixed rate of change. So in other words, your slope's the same every time. y2 minus y1 over x2 minus x1. So then if you go back to here, now we're going to go 2 minus 5, 2 minus 5 over 0 minus the -1. So we got -3 over 1, or -3. Well, that's got to be the same. Let me clean this up and look at right here. So you get -3. Now we're going to go -1 minus 2 over 1 minus 0. See how it shows it right there? You got -3. So every time you go y2 minus y1, every time you find the slope, you're going to get -3 every time. So this one's actually linear. A is linear. B we talked about, when you take the ratio of consecutive outputs, you end up with a growth rate of 1/2. This one was exponential. That was B. Third one was not exponential. We found that. But now we try and decipher, is this thing linear or not? Well, the first time when you find the slope between these 2 points, you get a slope of 2. Then you use these 2 points, you get a slope of 3. So this is neither. It's not linear, nor is this one exponential. Okay. Here's just an example in the everyday world. You kind of tell where I stole this. Copyright there, ending at 2013. This is Facebook subscribers year by year. And you notice if you were to put these on a graph, right, by year and number of Facebook subscribers, you'd see that exponential growth, right? These Facebook subscribers have grown exponentially. And now if you're looking at, well, what happens if you change the growth rate? So instead of 2 to the x, with 2 to the x, we had 1 comma 2, and then we had 2 comma 4. Anyways, it was kind of like this. Anyways, I can't draw very good. But if we increase it to a growth rate of 3, see the one in black, it's a little slower increasing initially than the 2 to the x, but then it takes off quicker, right? And then 6 to the x, again, after that point 0, 1, after that point, it takes off quicker. So as you increase the growth factor, it's going to increase quicker after that y-intercept of 0, 1. Okay, and every one of those, depending on the a, we started out with 2 to the x, so our a was 2, the growth factor. All of these, whenever your a is greater than 1 here, you're going to go through 1 comma a. So in this case, our a was 2, so it's going to go through 1 comma 2, and it's going to go into. It's also going to hit the point 1 over a when your x value is -1. Okay. And these are a big point. This is the point you always remember. When you've got exponential growth situation, anything to 0 powers 1. Okay, so remember, it's going to go through that. Depending on A, they're going to be looking a little bit different, but they're always going to go through that 0, 1, as long as you haven't moved them around, you know, right, left, up, down, any of that. Okay, they're going to go through that 0, 1. Well, let's look at it when our growth factor is a half. So now, instead of having an A value of greater than 1 like the other ones where we had exponential growth, what about when your A value is less than 1 but greater than 0? So in this case, the A value is 1/2. Let's throw 0 in. 1/2 to the 0 is still 1. Anything that 0 is 1. Let's throw a 1/2 in. Well, 1/2 to the 1 power, still 1/2. Let's throw a 2 in. So now we got 1/2 squares. So we got 1 squared over 2 squares. So we got 1/4. Throw a 3 in. We get 1/8. So let's plot these. We got 1, half, 2, 4, 3, an 8. So and 0, 1. So as we're going to the right, notice this thing's going to go lower and lower and lower. So we're going to have this horizontal asymptote. As we go to the left, now let's plug in some points, -1, -2, -3. So -1, -2, -3. Now we got 1/2 to the -1. So that's 1 to the -1 over 2 to the -1. So the 2 to the -1 goes up, becomes 2 to the 1. 1 to the -1 goes down, becomes 1 to the 1. So it's just 2 over 1. If you remember those. So you got -1, 2, plug in -2, you're going to have 1 to the -2 over 2 to the -2, so that ends up being 2 squared over 1 squared, which is 4, and so on with these. So you start graphing that, and you're like, oh my goodness, this thing is an exponential decay function. Okay, so you have an exponential decay situation where you've got that A less than 1 but greater than 0 situation. You still got this horizontal asymptote y equals 0, but when that value is between 1 and 0, you got exponential decay. Okay. Now, if you think about 2 to the x, if you just replace it with 2 to the -x, well, what's that going to do? It's going to take that and it's going to flip it about the y-axis there. Right? So you can transform these things. Right? If you're looking at some other exponential decays, when your A value, instead of an A value being 1/2, if it's 1/3, well, as you're going left, it's going to take off a little quicker. If you have that value get closer to 0, like 1/6, it's even a smaller value. As you're going left, it's going to go up even quicker, right? And then to the right, it kind of tapers off even slower. So again, this point 0, 1 is an important point for exponential growth and for exponential decay. And with exponential decay, again, the A value between 0 and 1, it's going to go through 1A this time. And, I'm sorry, still 1A, and still -1, 1 over A on that, just like with the exponential decay, except it looks differently on your graph, obviously, because your A is different. So let's graph this using transformations. So you want to think about, this is 2 to the -x minus 3. So think about, who's the parent function? Well, it's 2 to the x. So you're thinking about 2 to the x. Here's your old 2 to the x. Goes through 0, 1 right there. Looks kind of like that. It's an exponential growth function. First of all, what does the -x do? Well, instead of being in front of this thing, it's up there, right? So it's a composite function. You're inputting -x into it. So that's going to flip you about the y-axis. So now here's y equals 2 to the -x. And then you're just going to drop it down 3, because you got that -3. So vertical shift down 3. And I'm thinking about this point right here, right there, and I'm dropping it down 1, 2, 3, right there. Okay, so now it's going to go through that point. I'm also thinking about my horizontal asymptote y equals 0, and that's dropping down 1, 2, 3 as well. Okay, so reflection about the y-axis, drop it down 3. Here's a little bit better look at that. So you've got your horizontal asymptote y equals -3, and you can plot some points from there. All right, let's get into E, the famous irrational E. So many problems occur in nature require the use of an exponential function whose base is this irrational number E, like population growth, decay, savings, continuous compounding, Newton's law of cooling, heating. All of these things are stuff that involve e, okay? And so e is defined as the limit. This is using calculus here. The limit as n goes to infinity. This is saying as n gets increasingly large, you got your n right here and here, it will approach the value of e. Okay, so you've got this, if you can imagine this is some Microsoft Excel file or whatever, and you see how you're letting your n get larger here. And here's our, as we let n get larger on this 1 plus 1 over n to the n, it gets closer, more and more accurate to the actual e. So as we let n be 1, it's only 2. As we let n be 2, now it's 2.25. And it's getting closer and closer and closer to the actual value. In other words, less and less error. So this is pretty darn close. It's accurate out to, I don't know, let's say 4 or 5 spaces or what decimal places or so. But what I want you to remember is e, just like you know that pi is 3.14159 or 3.14, I want you to remember e is 2.718. Okay, memorize that. E is approximately 2.718. Okay, now you can use that to graph the famous exponential function e to the x. So now, still plug in some values. And remember, e is a number. It's an irrational number. So e to the 0 power is simply 1. Let's plug in 1 and 2. E to the 1, well, that's 2.718 because we memorized it. E to the second power, that's about 7.39. You grab your calculator, punch that in. E squared, it's about 7.39. You could keep going with that, but let's go to the left here. E to the negative 1, well, that's 1 over e. So that's about 1 over 2.718. That's about 1/3, whatever 1 over 2.718 is. Plug in negative 2. Well, that's e to the negative 2. That's 1 over e squared. That's 1 over 7.39. You keep graphing these. So you got 0, 1. 1 comma 2.718, it's about there. 2 comma 7.39, it's about right there. Negative 1, and I'm up about 1/3, 1 over 2.718. So I'm about 1/3 of the way up, about right there. Negative 2, I'm up about 1/7 of the way. Anyways, we keep going on this, but it looks, again, kind of like that 2 to the x. We still got that horizontal asymptote y equals 0. This is a little better look at e to the x power. You can transform this one just like you can transform any of these exponential functions. You're thinking about what does e to the x look like. Looks kind of like that 2 to the x. Right? Here's your e to the x. It's just a little steeper after 0, 1. What does that negative in front do? Well, that's going to flip that about the x-axis. So that's the first thing we're going to do, flip it about the x-axis. So here's y equals negative e to the x. And then you see that minus 3 right there. That's a composite function there. That x minus 3 is replacing the x. And so you're going to go right 3 from there. So I'm thinking about this point, because I'm thinking about the 0, 1 initially. I flipped it over. Now it's going there. I still have that horizontal asymptote y equals 0. Now I'm just moving that right 3. 1, 2, 3. So I'm moving it 1, 2, 3 to the right. So here's where it's going to go through. All right, now forget about that point. Okay, still got that same horizontal asymptote y equals 0 because I just moved it to the right. Here's a little bit better look at that. And you could graph some points with that as well. Okay. Now we'll do some basic solving in this section. So if a to the u equals a to the v, if you have the same base, well, u must obviously equal v. That's what your approach is going to be initially with these. For example, 3 to the x plus 1, if that equals 81. Think about 81. Can you rewrite that with a base of 3? Well, you're like, well, let's see. 9 squares 81, and I know 9 is 3 times 3. So 3 times 3 times 3 times 3, in other words, 3 to the 4th, is 81. Well, now they got the same basis. So x plus 1 must equal 4, subtract 1, x equals 3. You could plug that x equals 3 in, and you'll see that that's true. Over here, not so simple, because you can't write that 8 with a base of 4. But you can write 8 with a base of 2. 8 is 2 to the 3rd. And you can write that 4 as 2 squared. Now, power over power, you're going to multiply those. So you're going to have 2 to the 2 times 2x minus 1 equals 2 to the third, x plus 3. Go ahead and distribute those. And notice they both have a base of 2. So this 4x minus 2 has got to equal this 3x plus 9. Subtract 3x both sides. Add the 2. Oops, 9 plus 2 is 11. So we got x equals 11 on that. Okay. You can do it with the base of e as well. So you're going to work with this. You got a power over power. You got e to the 2x. This is 2x over 1. You got 1 over times 1 over e to the third. Multiply 1 times e to the 2x equals e to 2x. On the top, you got 1 times e to the third, e to the third. They're both e. So you've got to, you can use the division there. So you got 2x minus 3. Quotient of powers, I should say. Now they're both base e. Set them equal to each other. So negative x squared equals 2x minus 3. Solving a quadratic this time, so get one side equals 0. So 0 equals x squared plus 2x minus 3. Factor that, so you got x plus 3, x minus 1. So x equals negative 3, or x equals 1. You go ahead and you plug those both in to see which one of those, or if both of those work. You plug them back in. Negative 3 squared is 9, so you got e to the negative 9. Plug it in over here, you got e to the negative 3 times 2, so negative 6. E to the negative 6 over e to the third, negative 6 minus 3, e to the negative 9, so that'll work. Plug the 1 in. Similarly, that one's going to work as well in this case. Alright, well thanks for listening. We'll see you guys in class.